The force F acting on an object equals its mass m times its acceleration a. This relationship was proposed by Isaac Newton as the second of three laws for describing the motion of objects. It is also called the balance of linear momentum. Let's recap what it means. The force is a vector with three components. The mass is scalar and the acceleration is again a vector with three components. If an object with constant mass is at rest, and if no force is acting on the object, then the object's acceleration is zero and thus the object remains at rest. If a force is acting on the object, then the object accelerates in the direction of the force and the acceleration is equal to F divided by m. If the force is removed again, the object does not accelerate anymore and moves with a constant velocity until another force is acting on the object. Note that F here denotes the net force acting on the object. If more than one force is acting on the object, we have to sum all these forces. Therefore, the balance of linear momentum is sometimes written as the sum of all forces equals mass times acceleration. The balance of linear momentum is the backbone of classical mechanics. It can be used to describe the motion of objects dependent on the forces acting on the objects. But the balance of linear momentum in its classical form, sum of F equals m times a, has some limitations. It can only be used for rigid, undeformable objects. But what if we are interested in the deformation of matter? In continuum mechanics, we assume that different forces or stresses are acting at different points within the object, which means that different points in the object accelerate in different directions. And this is reflected in the deformation of the object. To relate the forces and stresses in an object to the acceleration of its points, we need to adapt the balance of linear momentum from classical mechanics into a form suitable for continuum mechanics. And this is exactly what we will do in this video. To formulate the balance of linear momentum in continuum mechanics, we need to consider which forces may be acting on an object. First of all, there may be tractions acting on the surface of the object, for instance when it is in contact with another object. The tractions are denoted by t, and they may be functions of space and time. The tractions represent forces per area. Let's denote the net force resulting from the tractions by Ft. To compute the net force, we have to integrate the tractions over the object's surface, which is denoted by partial omega. The dA in the surface integral represents an infinitesimal area element. Note that surface integrals are sometimes written with two integral signs. Here we just use one, which is a common convention in continuum mechanics. In addition to the tractions acting at the surface, there may also be forces acting within the interior of the object. These forces are called body forces, and they are denoted by B. Like the tractions, there may be functions of space and time. Because body forces represent forces per volume, it would be maybe more precise if we called them body force densities. But they are commonly called body forces, so we will stick to that. To compute the net force Fb resulting from the body forces, we have to integrate them over the object's volume. In the volume integral, the space occupied by the object is denoted by omega, and dV represents an infinitesimal volume element. Volume integrals are sometimes written with three integral signs, but we will just use one here. The most common example for a body force is the gravitational force. It is equal to the mass density of the object times the gravitational acceleration. But there are also other examples for body forces. For example, if the object is charged or magnetized, and it is near to another charge or magnet, there may be also electric or magnetic body forces acting on the object. The sum of all forces acting on the object is simply the net force resulting from the tractions plus the net force resulting from the body forces. Recall that in classical mechanics, the sum of all forces acting on an object equals its mass times acceleration. The balance of linear momentum in continuum mechanics is similar, but we have to slightly reformulate the right-hand side. In classical mechanics, objects are often simplified as point masses. This means that only the total mass of the object is considered. This changes in continuum mechanics, where we consider objects with mass densities that vary in space and time. Therefore, we define the mass density ρ, which represents the mass per volume at each point and at every moment in time. In classical mechanics, we also assume that objects are rigid, meaning that the acceleration is constant throughout the object. This assumption no longer holds in continuum mechanics. In continuum mechanics, acceleration becomes a function of both space and time. It is defined as the second time derivative of the displacement field u and describes how matter is accelerating at each point and at every moment in time. The balance of linear momentum in continuum mechanics states that the sum of forces acting on the object, that is Ft plus Fb, is equal to the volume integral of the mass density times the acceleration. If we expand Ft and Fb, we arrive at this expression. What we have arrived at is called the balance of linear momentum in its global form, where global means that we have considered the linear momentum accumulated over the entire object. However, in continuum mechanics, we are most often interested in a local form of the balance of linear momentum. That is, we are interested in the balance of linear momentum at each point in the object. To obtain the local form of the balance of linear momentum, we have to reformulate the global balance of linear momentum. So let's do this step by step. First of all, let's focus on the net force resulting from the tractions. Recall that the traction T is equal to the stress sigma times the outward unit normal vector n. The surface integral of T can thus be written as the surface integral of sigma times n. For the next step, we need the so-called divergence theorem, or Gauss's theorem. This theorem states that the surface integral of the stress times the outward unit normal vector is equal to the volume integral of the divergence of the stress, where the divergence of the stress, which is denoted by nabla dot sigma, is defined as a vector whose entries contain sums of the partial derivatives of sigma along each row of sigma. We will not formally prove the divergence theorem here, but I want to say a few words about it before we move on. The divergence theorem is interesting because it allows us to transform an integral over the object's surface into an integral over the object's volume. This relationship is somewhat unintuitive. Why can we deduce information at the boundary of the object from the information within its interior? To answer this question, we take a look at the fundamental theorem of analysis. The integral of the derivative of a function from a to b is equal to the function evaluated at b minus the function evaluated at a. Maybe you know this formula in a slightly different form. The integral of a function from a to b is equal to an antiderivative of the function evaluated at b minus the antiderivative evaluated at a. We can see that the fundamental theorem of analysis relates information in the interior of the interval from a to b to information at the boundary of this interval. The left-hand side can be interpreted as the accumulation of all the small changes of the function between a and b, and the right-hand side is the total change of the function between a and b. The divergence theorem can be seen as a generalization of the fundamental theorem of analysis to 3 dimensions. In 3 dimensions, instead of the derivative, we have the divergence, and instead of the boundary information at a and b, we get a surface integral over the boundary of the object. I hope this gives you some intuition about the divergence theorem. Hopefully we can discuss it in more detail in another video. But for now, let's move on with the balance of linear momentum. Let's substitute the divergence theorem into the balance of linear momentum. We observed that the resulting equation contains only volume integrals and no surface integral anymore. We can group all integrands of the volume integrals together to obtain one volume integral that must be 0. Now let's proceed with the final step in deriving the local form of the balance of linear momentum. From the fact that the integral of the divergence of sigma plus b minus rho times a is 0, we deduced that the integrand itself, that is the divergence of sigma plus b minus rho times a, is 0. This final step requires some explanation. Please note that this step is not a result purely derived from mathematical reasoning. If the integral of a function is 0, this does not necessarily mean that the function is 0. Instead, this final step comes from physical reasoning. We have derived the global balance of linear momentum for the entire object omega. But we could have also considered a smaller region inside omega. In that case, we would have arrived at the same result, with the only difference being that the volume integral would be taken over this smaller region, which I denote by lowercase omega. The key point is that the global balance of linear momentum must hold true for any smaller region inside omega. This means that the integral of the divergence of sigma plus b minus rho times a must be 0 for all possible regions lowercase omega. And this is only possible if the integrand itself is 0 everywhere. We finally arrived at the local form of the balance of linear momentum in continuum mechanics. Note that in continuum mechanics we are often interested in the deformation of an object after it reaches a stationary state, where the acceleration vanishes and the system is no longer changing in time. In that case, we obtain the quasi-static balance of linear momentum, where the quantities are time independent. Finally, I want to note that we have derived the local form of the balance of linear momentum from the global form. Some textbooks prefer to derive the local form directly from an infinitesimal volume element. I slightly prefer the derivation that I have shown you today, but I guess it's just a matter of taste. I will put a link to this other derivation in the description of the video in case you are interested. And by the way, in this video we only discussed the balance of linear momentum. Additionally, the balance of angular momentum must be fulfilled. We will not discuss it in detail in this video, but from the balance of angular momentum it can be derived that the stress tensor sigma must be symmetric. This means sigma 1, 2 must be equal to sigma 2, 1 and so on. As long as we always make sure that the stress tensor is symmetric, we guarantee the fulfillment of the balance of angular momentum. Throughout this series of videos on continuum mechanics, which so far focused mostly on solid mechanics, we have covered several concepts. We have learned about the strain tensor and how it can be derived from the displacements. We have introduced the stress tensor and a simple relation between the stress and the strain, the linear elastic material model. And in this video we have derived the balance of linear momentum. All these equations form together with some boundary conditions a boundary value problem. The primary variable of interest in this problem is the displacement field. Because if the displacement field is known, all other quantities can be computed from the displacement field quite easily. Solutions to the boundary value problem can only be derived by hand for simple geometries and simple boundary conditions. For complex geometries and boundary conditions, we have to use computational methods like the finite element method to find approximate solutions of the displacement field. With these computational methods, we can simulate the behavior of objects considering different geometries, different boundary conditions, and different material parameters, which makes such simulations a powerful tool in the fields of physics and engineering. That's all for this video. Thanks for watching, and I'll see you in the next one. Bye!